Uh, Good afternoon, everyone. Let's begin our session. This is week 7 of the mathematical methods in physics. So today we will be discussing about the concepts that were being discussed in the previous week, and also solve few problems that will help you solve the assignments given in the previous week. So let's begin our session. So please let me know if there is any problem with the audio. I think there is a echo, slightly echo. So apart from that, if that is creating any major issue, please let me know. And also, if there is any technical problem that my audio get disrupted, please that also let me know. Yeah, and if you have any doubt in between, also interrupt and ask. Yeah. The first concept that I will be discussing is the Laplace transforms. The previous week, this was mainly the content of the previous week's session. That was the Laplace transform. So in Laplace transform is basically given by this particular integral. So what we have here is Laplace transform of a function ft will be given as this integration of e to the power minus st ft dt. So that is what the Laplace transform is given as basically. So ft is a real valued function. Just hold on for a second. Yeah. Basically, this ft is a real valued function of the real variable t, and it is defined for t greater than 0. So that is the definition of the function ft, and the variable to which the Laplace transform is mapped, the Laplace transformation maps the function ft to a function which is given by this capital Fs. So the s is that value for which this particular integral is defined. So there will be certain values of s for which the integral will not converge, it will diverge. So we are not considering that range of s, but we are considering only that range of s where the integral is clearly converging. So that is the restriction on the s. So this is how we obtain a Laplace transform for a function f given by ft. We have to perform basically this particular integral and obtain the Laplace transform. So I have taken few examples that were being discussed in the class note itself. Can you please confirm if the echo is creating a major issue? Okay, thank you very much for confirming that. So let's continue. So I have taken this particular set of examples from the class note itself. So all this integral, all these examples, basically it's very simple calculation. So I'm not doing it anymore. Basically your function ft is this. So this is ft equal to 1, that is my function for the first example, and e to the power st. Yeah. So when you perform this integration, you get this value 1 upon s. So likewise, you carry out this integration for all other variables or all other functions. So in this case, the function is t. In this case, the function is exponential, sinusoidal, cosine. So basically you carry out all this integration, and this is what the some standard results that will be very helpful in your maximum problems that you solve in the Laplace transform. So I've just presented them here. So using this result, let's solve a few examples. Okay, so the first example is this. So you have the function ft given by this. So your ft is t raised to the power n, So you have to find out the Laplace transform of this function. So basically what you have to do is that you have to carry out this integration. So the integration is mainly 0 to infinity and your function. Yeah. So to solve this, first of all you make this substitution. So when you make this substitution, what you get is this. So here you see there is this particular integral. It is a very special integral. It is known as the gamma function actually. So this is, I'm writing here, this is the definition of the gamma function. So the expression of gamma function is that the integral goes from 0 to infinity and e raised to the power of minus x and x raised to the power n and then integration dx. So this particular integration is equal to n factorial. So let us use directly this result here. So s to the power n plus 1, here it should be. Yeah, n plus 1. So what we get is x n factorial So we got to derive this particular form. So from here you can check that when your n is equal to 1, so when n is equal to 1, then your function ft is nothing but just t. So from here you can conclude that Laplace transform of t is equal to 1 factorial s square. So it is 1 by s square. Yeah. So that is what we also derived here, mentioned here also. So it is, this formula is kind of very general formula because when you put n is equal to 0, ft becomes 1. So then what you see is Laplace transformation of 1. Just put n equal to 0, you have 0 factorial by s, that is 1 by s. So if you keep this result in mind, that this particular result, then for any value of n you can easily get the Laplace transform. Yeah. Now let us look at this particular example. So in this particular example, the definition has been divided into two parts. Like the same function has two different definition in two different range. So That implies that our integral will be divided into two parts actually. So Laplace transformation of this particular function will be 0 to k limit. It will be this function definition, and then for t greater than k, that is from k to infinity, its definition is just 1. So this is what the integration is. Yeah. So from the first integral, what you have is 0k t let us do the first integral by integration by part. So it's a very simple integration. So first of all, you will have t e to the power minus st, then you have minus of s, zero k, yeah, and then in the other part you have yeah. So that is from the first part, and from the second part you have so you have minus of 1 by s, yeah. So on putting every limit here, what you get to see is 1 by k. From the first term it will be like k, yeah. This lower limit I did not put because t equal to 0 it vanished, and this 2 came from here. So okay, and in the remaining part it was this is it became plus because infinity that is equal to 0, so only the lower limit remains. So this is what we get. So from here you see this k and this k will cancel, so that will cancel with this. So ultimately what we have is this k comes here, so minus 1 by k s square e to the power minus sk, and then plus 1 by k s square. So let's take this 1 by s square outside. So I have, yeah, so basically the only change here was that the function has two different definition at two different interval. So depending upon the interval we put the function definition and obtain the value of the integral. So that gave me the Laplace transform. So all that was pretty straightforward because all we need to do is just calculate the integral. So but there are various properties of the Laplace transform. like that will help you perform the Laplace transform of various complicated function, like without having to do the integration all the time. You can use this property and then break down your problem into a simpler part. So let's look into the properties. So the first property is the linearity property. So this Laplace transform operation is a linear operation. That implies that suppose you have one function known as this f1 and the other function is f2, and their corresponding Laplace transform is capital F1 and capital F2. So the Laplace transform of a linear combination of the given function, that is c1 f1 plus c2 f2, that is a linear combination of two function f1 and f2. So the Laplace transform of this linear combination is equal to the linear combination of the Laplace transform of the individual function. So Laplace transform of this total function, like linear combination, is equal to the linear combination of the Laplace transform of the individual functions. So f1 was Laplace transform of small f1 and f2 was Laplace transform of small f2. Small f2. Yeah. So that was one property about the linearity. Next property is the translation property. Translation property means that suppose you know the Laplace transform of a given function f. Suppose the Laplace transform of a given function f is known to be capital F of s. Okay, so Laplace transform of a given function, it's a capital F of s. So when you suppose you multiply exponential of at into the function, so now you modify your function into this form. So when you do that, you basically the Laplace transform of this resultant function is the same as the original function, Laplace transform of the original function, just that the argument is displaced by the constant a. So whatever was the Laplace transform of the original function, it remains the same as that, but the argument is no longer s, it is s minus a. So basically you will just replace your s with s minus a and you will get the Laplace transform of this particular function. So that is the translation property, because we are shifting shifting my Laplace transform of the original function by a distance a. So that is about the translation property. Next is the difference, what we do obtain when we differentiate the Laplace transform. Okay, so this property is nothing but like suppose you have a function ft whose Laplace transform is given by fs again. And suppose you want to find the Laplace transform of this t raised to the power n into ft. So that is given by differentiating this particular function, whatever you had, like Laplace transform of the original function, nth times with respect to s, so and multiplied by minus 1 to the power n. So that's about this property. Mainly your this linearity property and this translational property will be very helpful in solving few problem. Let's discuss that problem based upon that property. So Yeah. So this is the problem I have. So I have to find the Laplace transform of t square cos at. So one way to do this is to simply perform this integration cos at into e to the power of minus st dt 0 to infinity. One way is the traditional method, that is to perform this integration and get the value of this integration. So that would be the Laplace transform. But we are being asked that we should use the linearity property and then obtain this particular integration. So in that way it will reduce our effort. So we don't have to carry out this like difficult integration. So let's see how the linearity property will reduce down our effort. So basically your cos at, if you write it in a Euler form, so in complex Euler notation, so that will be given by this thing. Yeah, now use your linearity property and split it. Use yeah. So now we what we have to do is we have to find the Laplace transform of this particular thing. Okay. So now another property we can use that we learned earlier, just few minutes ago we learned, is the translation property. So let us use that. Okay. So your translation property, let me bring this here. So this was your translation property. So if you compare, if you compare this with the function you have in hand, so what is you have is ft is basically t square, and your a is ia. Yeah, so that is the change you have, and I already said capital F is the capital Fs is the Laplace transform of the function ft. So here you need the Laplace transform of t square. So Laplace transform of t square is, again remember we derived one very general equation here. So Laplace transform of so here is something we derived. So if we use this there, so here in that place n is equal to 2. So that will be basically yeah. So you have obtained this Fs. Now you can easily obtain that s of minus a. So that will be 2s minus ia cube. So you have obtained this result. So we have just used the various properties. We did not use any kind of difficult integration. So similarly you can also get for the second term. So from here what you have is Laplace transform of Yeah. Similarly, you can also have Laplace transform. You can carry out this yourself and can see that Laplace transform of minus iat. So the only change would be, in place of a changing to ia, a would change to minus ia. So that is why it will be in the denominator, it will be s plus ia cube. So we have obtained these two form. So let us substitute back here, okay, and get the resultant form. So result would be equal to half of yeah. So this is what the result is. You can simplify further and bring it down to a more cleaner notation, but this is what the result is. So basically here what we did is, we did not carry out any difficult integration. So what we used the linearity property first of all. That was very straightforward, linearity property, and immediately we could use our translation property. And also we used our result from the previous example, some general result we used. So using these three results, we could easily write down the Laplace transform of a complicated function. So that is the beauty of knowing the various properties of Laplace transform. You don't have to carry out the difficult integrations. Okay. So with that, let us go to the next topic, that is Heaviside step function. So step function basically looks like this essentially, because it looks like a step first of all, and the main property is that for certain values of argument, the value of the function is 1, and for values below a threshold, the value of the function is 0. So here the threshold is a. So what we see from the graph is, for t greater than a, so for this region, the value of the function is 1. So this blue line is the value of the function, it is always 1. But for value less than a, your value of the function is 0. So that is what is being denoted here by this notation. That is, for t greater than a it is 1, for t less than a it is 0. Yeah, so this is also like very trivial case, that the Laplace transform of a step function is simply this. That is the usual definition. Now incorporating this particular definition of the step function, we are left with this integral. So after carrying out the integral, we get to know that this is the Laplace transform of a step function. So just remember this particular result. So what you see here is that the threshold value appears in the exponential. So if your threshold value was 2, suppose a is equal to 2, then the form of this would be 2s by s. So keep that in mind, that depending upon the threshold, how this form will change. Otherwise the form is same almost everywhere, like e to the power minus as by s. So another special case you can actually see here is that, suppose you take your threshold to be 0. Okay, so when you take your threshold to be 0, so how does the graph changes? The graph becomes this. This is how the graph becomes. So what this graph essentially is that this is constant graph, that is 1 for all values greater than 0. So remember our definition of the Laplace transform was defined such that the value of t always has to be greater than 0. That is, negative value of t is not allowed anywhere. So all values of t is always greater than 0. So essentially this particular special case of step function is nothing but a constant function. So we saw earlier that the Laplace transform of a constant function is 1 by s. So that result is also recovered that result from this also. So if you put a equal to 0, you get 1 by s. So this we saw earlier. Yeah, so that was with the step function. Now another is properties of translation of a function. That is, you're moving a function by certain distance. So let's take one case of function. So I can draw my function to be, let's say, my function was like this. So it is a sine curve sine x. Okay, now I can shift my function, that is translate my function along x axis. Yeah. So what did I do here? I translated my function by pi by 2 distance along the x-axis. So you can consider that gt. So if I write t here as the variable, everywhere t let me write, because t is what I am considering. Yeah, so gt is 0, so this, it is 0 here. For t lying between 0 to pi by 2. Okay, and it is so f t minus pi by 2 for t greater than pi by 2, and your ft is sine t. Yeah. So it is clear, right, from this that you have a function sine t. You have a function sine t, and then you shifted your function by for certain distance pi by 2, and you get a new definition of the function. So that definition of the function is gt. So how is gt related to the old function ft? So that relation is given by this definition, that is, it is 0 for values of t less than pi by 2, and for values of t greater than pi by 2 it takes this form, ft minus pi by 2 in the argument. So that is how these two functions are related. So we are interested in finding what is the Laplace transform of this shifted function. So what is the Laplace transform of this gt? So can we express it in terms of Laplace transform of ft? Can that be done? So we are interested in knowing that. So let us see. Yeah, so what we had is our function ft, and we shifted by some distance. T equal to a, we shifted by some distance t equal to a and got gt. Now we are interested in knowing how is Laplace transform of gt related to the Laplace transform of ft. Simply they are related by this. Yeah. So just with this addition, this multiplicative factor e to the power minus as, where a is the distance by which the function has been shifted. Yeah. So how did we come to this form? So how could we actually derive that this is what is the correct expression? So that can be achievable. So wait. Let me go to next page. Yeah. So we defined a step function in between actually. So here is the step function. So that step function says that for values less than a, my step function is 0. Okay, so that is why the function becomes 0. And for values greater than a, the definition is this. So in one line we could express our gt as this format. So after that we perform the traditional integral, that is f t minus a ut minus a e to the power minus st dt. Yeah, and then it would be like we have infinity here. So what we have is for t less than a, this thing is 0, so we don't consider. And next thing is we have to consider from a to infinity, we have ft minus a e to the power minus st dt. Okay, so we make a substitution right now. T minus a is equal to x. So when we do that, what we have is basically e to the power minus s of this x plus a. So dt becomes equal to dx. A becomes 0. So lower limit becomes 0 and the upper limit continues to remain infinity, and we have f of x. Yeah, so we have SA and the remaining term is just Laplace transform of fx. So this is how we could prove this. So this particular property will also be helpful in arriving at many results. So let us keep that in mind. So let's move to this next question. So this is a graph problem. So there's nothing, this is not going involving Laplace transform or anything, but it will help you visualize what is step function. Okay, so first of all you have to draw the graph of this step function. So there are two step functions involved there, and the total is the difference of the two step function. So let us draw this first of all. Okay, so this is my t-axis. So the first step function is ut minus a. So what is the definition of this? For t greater than a, it is 1, but for t less than a, it is 0. So that is from the definition of step function. So that says that if I pick this point as a, so if I pick this point as a, so for values of t greater than a, ut minus a continues to be 1. So this is my graph of ut minus a. Now let us go towards the next term. So that says that for t greater than b, it is 1, for t less than b, it is 0. And we are being said that b is greater than a. So obviously B lies somewhere here. So from this definition, let me pick a different color. So from this definition, what we get to see is that for t greater than b, this is my definition, like definition of ut minus b. Yeah. So if we subtract them, what will be the resultant part? So can you say which part will be the resultant part in this? Like if I have to find ut minus a, ut minus b. So that is equal to like what is that equal to, and within which range that is defined? Just say me within which range it will be defined, like non-zero. Yeah, so you're correct. Between A and B it will be non-zero, and in all other place it will be 0. So yeah. Yeah, within only this range it will be defined, that is between point A to B, and in all other place it will be equal to 0. Yeah. So that is the definition of this kind of step function. So actually this kind of step function will be very helpful when you are said to express any kind of function in terms of step function. Suppose like let's say for example you are given a function definition, okay, like let's say that you are given that sine 2x fx is sine 2x in between 3 to 5, and it takes cos 2x in between 7 to 8. So easily you can pick out these ranges. So you know that your step function is non-zero within this A and B. So if you, for this particular first part, if you just write that A is equal to 3, B is equal to 5, then you can write your fx to be sine 2x ux minus 3 minus ux minus 5, and the next part also you know that it is given that cos 2x is only valid in this range. So you can easily write x minus 7 minus ux minus 8. So what you have achieved, that you have achieved expressing this particular function in a common notation. In one line you could write everything. So that you achieved by using this step function. So I hope this part is clear how I could write this, because this will be very helpful in the next examples. Yeah. So this is one example. So similarly here you see the definition is divided into two parts in two ranges. So first of all it has been asked to express the function in terms of unit step function, and then you have to find the Laplace transform. So first of all let us write in terms of the first unit function has to be defined in which range? Can you just write, like, we definitely require two step function. So first one has to be defined within 1 and 2, right? So it will have ut minus 1 minus ut minus 2. That is one term I need of the step function. So that will couple with this particular part. Okay. And the next part is 3 minus t. Here ut minus 2 . Yeah. So this is how we are writing in terms of unit step function. So the first part of the question is done. So first part was to write in terms of unit step function. So this is my equal to ft. Now let us find the Laplace transform. So Laplace transform, now it will be very easy to find because we have already expressed in terms of unit function. So let us simplify this a bit, okay, because some terms are there which will get cancelled. So yeah, so ut minus 2 is common over here, and then we have this minus of t plus 1 minus of t plus 3 we have here. So that would be a minus 2t plus 4. Yeah, also, like, we can take minus 2 common. Minus 2 we are taking common, then we have this. Yeah. And then last term can be written as t minus, so minus we took common and then we have this. So this is the like the resultant form of this. So remember we had learnt a property of this step function. So that property was here. So we will use this property and easily get to our problem. So in this case, basically your ft is t. So you can write lambda of Laplace transform of t is known to be 1 by a square. You already know this. So let us use this here. Yeah, and gt was t minus 1. Yeah. So in all this case your a is 1. For the first term it is 1. And for the second term, remember this was the definition of GT. Yeah, so this was the definition of GT. Let me also bring this here so it will be easier for you to understand. Uh, yeah. So this was the GT involved here. So wherever GT you see, yeah, wherever GT you see, that is basically this. So using this you can compare. So first term is t minus 1 u t minus 1. So if you compare this with this GT, what do you say? Like, what is the value of A? Can you say it is 1? Okay. Now semi for the second. Okay, like what is the value of A in the second? And also for the 3. Yeah, what is the value of A? What is the value of A for the second and third? It's very simple. Yeah, it's 2 and 3. That's simple as that. So you are just comparing like with this. The value is 1, 2 and 3. So ft is t here basically. So you're replacing t with t minus 1. Then it is becoming t minus 1 here. So ft is equal to t. So from this formula, Laplace transform of ft is something you need to know. So Laplace transform of t is 1 by a square. So for the first term, Laplace transform of the first term, I'm not writing it explicitly, so but for the first term, that is for this term, it is given as e to the power minus as, and your a is 1, so e to the power minus as a square. Similarly, Laplace transform for the second term also can be written and also Laplace transform for the third term. So Laplace transform for the second term, a is 2. So basically you have this 2 over here and 3. So that's all. Like, so now the result is very simple. It is e to the power minus s by s square minus 2s by s square yeah. So that is your result. I hope that example was clear. There was no problem in that, right? So let us go to the next topic, which is the periodic function. So periodic function, we are given with a function ft, and we are said that it has a period capital T. So we don't have to carry out when we are asked to find out the Laplace transform of this periodic function. So we don't have to carry out the integration over the entire range from 0 to infinity. What we just have to do is carry out the integration over this range, that is over a period, that is 0 to capital T. So inner definition remains the same, like whatever it remains with the Laplace transform, that's basically the same, that is ft to the power minus st dt. But the range of integration is different, it is in one period. But there is a prefactor that comes, that is 1 by 1 minus e to the power minus capital Ts. So that this is where the time period comes. So I hope that is clear. So let's use this for this particular problem. Yeah. So here you see it is a periodic function, right? I have denoted it through this graph. This is a periodic function. So can you please say what is the period of this function? Because we need to know the period before we can go on to calculate the Laplace transform. So just say me what is capital T here? What is the period? Can you please unmute and say what is the period, because I'm not able to hear.
Sir, 2 pi by w.
Yeah, that is correct. So someone asked one question in the chat box, like what is the format of final exam, subjective or objective, MSQ, CVT. Actually, I'm not aware about the format. Most probably it will be objective, because your assignments are also objective. So I'm not sure, but if I get to know, I'll let you know in the next class. Okay. So yeah, so 2 pi by omega is the period. So let me just substitute capital T everywhere. And also split it over this entire period 2 pi by omega. Your function has two definitions. So for the first part, that is 0 to pi by omega, it is equal to sine omega t. And for the next part, it is 0. So basically you don't need to carry out the integration out there. So this is an integration you have to work out. So it is a very standard integration. Like we also have come across this integration in Fourier transform, if you remember, in the previous week's class, I think. Not in the previous week, but in the Fourier transform class. So it was. So this is given by yeah. So for this problem you have A is equal to minus S basically, and your B is equal to omega. So and other part is yeah. So your T is upper limit based upon T. So when you put the upper limit and lower limit, I'm not putting it and explicitly showing you, but ultimately you get this form basically. Yeah. Yeah, so that's all for this problem, because the period was given and we could just work out between that particular period, not over the entire range. And also you see it has no meaning in carrying out the integration from 0 to infinity, because ultimately the function repeats. That is one, like intuitively you could say, and also mathematically t equal to 0 and t equal to infinity is something, t equal to infinity and putting sine infinity and cos infinity, that would divert, so that would also not make any sense. So whenever you see a periodic function, you try to know the period and then carry out the integration within that period. Yeah. So let us come to this next topic. This is inverse Laplace transform. So basically, like you get, if you this is given that this is a Laplace transform of some function, unknown function. So basically by this inverse Laplace transform, what we are trying to get is what is the function of which this is the Laplace transform. So basically Laplace transform of ft is known, given to be this. So we are asked what is ft. Yeah. So let us try to reduce it down to forms which we know, like Laplace transform of, we know certain forms of Laplace transform. So we will try to reduce it down to that form. Otherwise it is very difficult to conclude of which function it is the Laplace transform. So let us first focus on that, how to reduce it down to a known form. Okay, so by the method of like partial fraction, we can reduce this total fraction in terms of various parts. So each of this part I hope you are aware about this method of reducing it down to partial fraction. So now your main task is to find A, B, C and D. So once you know the values of A, B, C and D, then you have this individually, you know, like this is one part, this is another part, this is the third part. So then you can conclude the function of which these are the Laplace transforms. So first of all, let us find out what is A, B and C, D. what are they? So yeah. So now the hand rule is to put, first step is to put the root of the first root of the expression present in the denominator of the first term. So s, if you were to solve s equal to 0 equation, what is the root of it? Obviously you can conclude 0 is the root. Similarly s minus 1, what is the root of it? It is 1 is the root of this particular denominator. So we can put first of all s equal to 0. So what advantage we get is that everywhere s that occurs in the numerator of the other terms, that get vanished. So second and third term, second term and third term gets vanished, and you have 4 is equal to a minus 1 4. So that give a is equal to minus 1. Yeah. Now put s is equal to 1. So when you put s equal to 1, this gets vanished, this also gets vanished. So you have 1 plus 4 so b is here equal to 1. Now what you can do, you can either put your root of this, that is s square plus 4, it will be plus minus 2i is the root. So when you put here and also put here, so and you try to compare the imaginary and the real part, so with that you can get the value of c and d. So I'm straight away writing the value. So putting s equal to so 2i, I think, plus minus 2i yeah. So with that you get the value of c and d. So basically your c comes out to be 0 and your d comes out to be minus 1. So with that you get the value of all this a b c d. So and you have your function, that is fs. So since it's a Laplace transform, let me denote it by capital F. So your fs is basically minus 1 by s plus 1 by s minus 1 minus 1 by a square plus 4. So you have split it into different fractions. Now you perform the inverse Laplace transform on this. That is L inverse of minus 1 by s just like your Laplace transform operation was linear, so this operation is also linear. Yeah. Can bring this minus outside. Yeah. So L inverse 1 by s. Remember 1 by s was the Laplace transform of which function? It was Laplace transform of constant 1. Similarly 1 by s minus 1 that was Laplace transform of which function? Yeah. And the other was the Laplace transform of, so basically here 2 if you add, so the form becomes very much clear now. This is the Laplace transform of sine 2t. So all this I could say from here, like in the first table I remember I gave these forms. So I said this is some important result. So from this result and from this result we could write the last two term, and this was the first term. So these are some important results. If you keep in mind, it will be very helpful, especially in inverse Laplace transform where you have to go the backward you have to go. So unless you know, it will be very difficult. Yeah. Yeah. So this was the three forms. This is the inverse Laplace transform of this function. So inverse Laplace transform of this ft gave this. Yeah. Now let us quickly come to the next part, which is convolution of functions. So this convolution of function is operation is given by this. So this asterisk is not usual multiplication, it is the convolution operator. So it has this form. So and you can either like you can make a substitution that t minus x to be some variable and then bring it down to this form. So and you see that this form is basically equal to this. So from this you can conclude that convolution operation is symmetric. It does not matter in which order you do the convolution operation, whether ft first or gt first, basically they are same. So for this context, the convolution function where it will be important here is in this this property that you see. This property is basically Laplace transform of two convoluted function, that is ft asterisk gt. So Laplace transform of two convoluted function is equal to the product of the individual Laplace transform. So this is not asterisk again. So this is just normal product. Yeah. So now let's take inverse Laplace transform on both sides actually. So when you take inverse Laplace transform on both sides, what you get is ft convoluted with gt is basically inverse Laplace transform of this entire thing. Okay, let me just write Laplace of ft Laplace of gt. So what you get to know is that one thing is sure, that this convolution operator has two definitions. Either you could follow this approach, that is perform the integration, or you could find out the inverse Laplace transform of this product. So this is the two property that will be helpful. So how it will be helpful in this context, it is to find out the inverse Laplace transform. So the problem where it will be helpful is, see here you could see that one thing you could clearly see, that the argument is appearing in this format, right? And this individually they are Laplace transform of sine. Sorry, the Laplace transform of sine was this a square plus a square, but Laplace transform of cos was s square plus a square. So they are Laplace transform of cos at, and this is Laplace transform of cos bt. Right? Yeah. So when you are said that you are asked to find out this inverse of this inverse of this, and now from this property you know that this RHS is equal to this convolution of two function. So here the function is cos AT and cos BT. So basically cos AT cos BT. So if you can determine what is the convolution of these two function, then you get to know the inverse Laplace transform of this original function, this entire function. So what you just did, you figured out that the argument was indeed product of two Laplace transform. So once you could figure out, you could sense that the function where cos AT and cos BT, you just now have to find out the convolution operation. So the convolution operation is the definition. From the definition itself you can write, in no matter how you write it, so you can either write cos AT first and cos BT later, or in the reverse way, but let me form this because they are symmetric, as I said. Yeah. Now you just have to carry out this integration. So using the trigonometric property, I can easily write this will be my one term plus yeah. So now the integration is very trivial. You just have to integrate cos and under cos. So when you perform the integration and put the x limit as 0 to t, so ultimately you get this expression. I'm not working out this simple integration. You can later do it. Yeah. So this is how you could find out the inverse Laplace transform using the convolution theorem. So it's a very important tool, because we initially saw that carrying out inverse Laplace transform is not such a trivial task. Either you should know the form, some standard form, otherwise it's very difficult to approach. So this is one of the tools that will be helpful. Yeah. Now with that, let us come to this another important topic, that is Dirac delta function. So the graph of the Dirac delta function looks like this. So it is everywhere 0 except at a point at x equal to a, let's say from the definition, it goes to infinity. So that is what the Dirac delta function is, and two properties are that when you integrate over all space minus infinity to infinity, the area under the curve is always unity. And the another next property is that you multiply a function gx with the Dirac delta and you integrate over the entire space. The integration is the value of the function at x equal to a. So this is the second property. These two are important defining properties of the Dirac delta. Now, yeah, these are the few properties that will be helpful. So first property is finding out the derivative of the delta function. So this is one property. So nth derivative of the Dirac delta multiplied with some function phi x is given as this, and Dirac delta function is even. This is one more property. This is like multiplication of x minus a and x minus b as an argument in the Dirac delta is given as this, and some general function fx present as the argument of Dirac delta can be written as this. So with some example this will be much more sensible to look at. So let us quickly go to the example first of all. So here your fx is given. So fx is x square minus pi square. Yeah. So what you get to see, you know your a and b right now. Okay, so Dirac delta of x square minus pi square is equal to 1 by 2 pi and this del of x minus a plus del of x minus b. So your a is pi and b is minus pi. So you can write x minus pi x plus pi. Yeah. So with that definition you can easily carry out the integration now, that dx cos x 1 by 2 pi and there is cos x is this, and so 1 by 2 pi from the first term, from the defining property of the Dirac delta, the first term would be cos pi and second term will also be cos minus pi it will be. So since cosine is an even function, both of them are cos pi, and cos pi plus cos pi is minus 2 by 2 pi. Sorry. Yeah, so that is my answer to this. Yeah. Now let me solve this. So in this basically you have to, so in this your fx is sine pi x. So we have to use this property. This property. So your f, so xi were the locations where fx vanishes. So fx equal to 0, that is equal to sine pi x becoming equal to 0. that is sine n pi. So your x is equal to n, where n goes to 0, plus minus 1, plus minus 2, all this. So and let's calculate the first derivative. First derivative is cos pi x with pi in front. So with all this prescription, what you have is delta of sine pi x summation over all xi. So your xi is this values of n, so 0, plus minus 1, plus minus 2. So this is my denominator. In the numerator you have delta function at various xi. There is mod. So basically you have 1 by pi and sum of various delta function, that is delta x for xi equal to 0, and delta x minus 1, delta x plus 1, and all other terms. So the numerator cos pi xi, mod of cos pi xi for all values of xi is equal to 1 for all values of xi. So this is what is sine pi x. Now the integration can be carried out like so the integration had pi in front, so 1 by pi exponential of minus mod x, and then this delta x minus 1, delta x plus 1, all this. So pi and pi cancels, and whatever remains is exponential of, first term is definitely exponential of 0, next term is exponential of 1, then exponential of minus 1. Yeah, there is always this minus present and mod of mod x. So the next term would be exponential of minus of 2, exponential of minus of 2, and so on. So basically you have 1 plus 2 e to the power minus 1, 2 e to the power minus 2, and so on. Now let us come to this next question quickly. So in the next question we have to there is a derivative involved, so we will use this particular formula. We'll use this formula here. So in this case what we have is let us just compare quickly. Your n is 2, right? Your n is 2, and your phi x is cos hyperbolic. Okay, cos hyperbolic function, cos hyperbolic x, and your a is 1. So this is just you got by comparing. So basically the integration is this part. So basically minus 1 to the power that is 2, then you have to take twice derivative of cos hyperbolic x, that is what it is said, and evaluate it at x equal to a, that is x equal to 1. So let us differentiate once cos hyperbolic x. Cos hyperbolic x differentiation is actually sin hyperbolic x, and second time derivative of cos hyperbolic x again gives cos hyperbolic x. So its value at x equal to 1 is basically cos hyperbolic 1. Yeah, so with that our this thing becomes equal to cos hyperbolic 1. So basically our integration result is cos hyperbolic 1. Yeah, so we have used mainly three properties here just to review this. First of all, this derivative property in the last question, and then this property, and again in this property. I hope that's clear. Now let us quickly go to how the Laplace transform would help you find the solve the differential equation. So that is something very important. So let us focus our attention on this for the remaining 30 minutes. Okay. So first thing is that Laplace transform of first derivative of a function. So ft is a function. So ddt of ft, what is the Laplace transform of this first order derivative? So that is equal to this s Laplace transform of that function minus the value of the function at t equal to 0. So that is for the first derivative. Now we can generalize this for nth derivative actually. So this is the expression for the nth derivative. So from this let us extract what will be the result for second order derivative, because we will be dealing with second order derivative problem. Okay, as we discussed in the previous class also, like second order differential equation. So from this what we say is that put n equal to 2. So we put n equal to 2, the first term remains, so that is given as this. N equal to 2 when we put here, then it will become minus s f0, and then in the third term we put n equal to let's say we put n equal to 2, then it becomes s equal to 0 and f1 of 0, that the first order derivative of f. So this is df of dt at t equal to 0, and that's all. Like no longer other terms do not exist for second order derivative. For third order derivative, next term will continue to remain, but let us focus our attention on these two results. Okay, so mainly we will be requiring these two results, so let me write it separately. So this is the one result that we will require. And this is another that you will require. So with this you can solve differential equations knowing this Laplace transform of the function. So this is first example. So let's take this example. So in this example what you have is a step function on the right hand side. So so this is my differential equation. ut minus 3 is a step function. So let us take Laplace transform on both sides. Yeah. So when you take the Laplace transform on both sides, basically the first this second order derivative is there in the first term. So this particular form is important. So we have s square Laplace transform of y minus s, value of function at 0, minus first order derivative evaluated at the 0. So that is from the first term. The second term is Laplace transform of the function itself. And in the right hand side you have to carry out Laplace transform of the step function. So from the previous exercises we can write this to be e to the power minus 3s by s. So because the threshold is at 3, remember I said you have to keep in mind just the threshold. So that is what the threshold 3 I have put here. So that is with the like yeah. Now let us put the values that are given, the initial boundary condition, that is at t equal to 0 the value of the function is 0 and the value of the first order derivative both of them are 0. So when we put both of them to be 0, then we have this two term gets vanished actually. So what we have, s square yeah. So we have this plus 9 of Laplace transform of y yeah. We can take Laplace transform of y common and that would be equal to a square plus 9 yeah. Now to know the function y, basically you have to perform inverse Laplace transform again. Yeah, something like this you have to find. So so again there is something to note here. So what you see, like you see 9 of s square plus 9. So this you can actually split into 3 into 1 by s into 3 by s square plus 9. So can you say this is the Laplace transform of which function? 1 by s. And this is of which function? So 1 by s is the Laplace transform of 1 and this 3 by s square plus 9, that is Laplace transform of sine. Yeah. So in a way you could for a moment you can ignore the exponential, because exponential like that is coming because of the shift in the function, so that you can deal with later. But ignoring the exponential, what you have is like 3 of 3 by s square plus 9 Laplace transform of 1 in one part and Laplace transform of sine 3t in the other part. Okay, now use the property of convolution. Okay, if you use the property of convolution, this will be equal to 1 convoluted with sine 3t. So that is, if you use the definition of convolution, so one function is just a constant, so mainly you will have just sine 3x dx. So from this you get after carrying out the integration you get this. Now you see y is equal to Laplace, what your y was this, inverse Laplace transform of 9 e to the power minus 3s s square plus 9. And you got to figure out that a part of it, that is excluding the exponential, you have this. Just excluding the exponential, you know the other is the Laplace transform 1 minus cos 3t. Yeah. So from the property, the shifting property, that is we learned here, that is the step function that we learned. Yeah, so from this property you can see, like you have gt given, so yeah, so so basically you have this thing given, so Laplace transform of ft and e to the power of minus 3s given. So obviously this is, from this result you can conclude that this is Laplace inverse of Laplace transform of function gt. So that is nothing but gt itself. And definition of, what was the definition of gt? It was ut minus 3 and ft minus 3. That is the shifted version. So your ft was 1 minus cos 3t. So your ft was 1 minus cos 3t. So your ft minus 3 will be 1 minus cos t minus 3 u t minus 3. So this is your y. So so this is how you solve the differential equation and got the solution. I hope this was clear. This was a bit lengthy and quite complicated also. I hope you could follow this. If you have any doubt right now, you can just unmute and ask me which part you did not understand. Okay, this last one example, then otherwise I will wait later for the question. You can ask both this question together because this is also a bit lengthy. So Here you have two simultaneous differential equation and two conditions, and you have to solve them. So first differential equation is second differential equation is given by this. So let this be named as 1, this be named as 2. So you take Laplace transform on both sides, okay. So when you take Laplace transform on both sides, so remember this is a first order derivative is there. So we got to use this result. Yeah, using this, what we can write is so let me write Laplace transform of so first of all it is from the first equation it is s of Laplace transform of xt at t equal to 0, what is the value, and then Laplace transform of again Laplace transform of yt. This is from the first equation. From the second equation what you have is same format, Laplace transform of yt y value of y at t equal to 0 minus Laplace transform of xt. So now you put the boundary condition value you have. So it is at a t equal to 0, x is 1, at t equal to 0, y is 0. So when you put that value, here only I am putting it. So this will become 1 and this will become 0. Yeah. So from here what you get to see is that Laplace transform of yt or you can say Laplace transform of xt is nothing but s into Laplace transform of yt. So just put this, I am calling this to be 3 and this to be 4. Put 4 in 3 and then you can write Laplace transform of xt to be equal to s by 1 plus s square. I did nothing, I just put this xt here and then this equation was purely in terms of yt, purely in terms of yt. Sorry, just hold on a second. So xt is this, yeah. Yeah, when we put this in equation 3, we have s of s square of lyt, yeah, s square of lyt plus lyt equal to 0. So lyt is So something is missing, I think this, just hold on. Okay. So from this expression itself, you get Lyt to be equal to, oh, this was 1, this was not 0. Okay, that was the thing I was missing. So it is 1, I was taking it to be 0. So let's put Lyt instead. So Lyt would be this 1 minus s of Lxt. So this I obtained from 3. Yeah, from 3 this I could get. So your L of like Laplace transform of xt would be s by 1 plus s square. So that would be xt is equal to Laplace transform of s by 1 plus s square. So which is equal to cos t. Okay. Yeah. So now let us call me this equation 4. Now put 4 this to be 4 and this to be 5. Put equation 5 in 4. What you have is Lyt is equal to one by s of Lxt. That is s 1 by s of into s by 1 plus s square. 1 plus s square. So this is Laplace inverse of 1 by 1 plus s square. So that is my sine function, sine t. So you have obtained xt and yt. So that is what you have to obtain. Xt is equal to cos t and yt is equal to sine t. Yeah. So if you have any problem in these two particular problem, please let me know anywhere you got confused or stuck. So let me revise this this two problem. Okay, so we had this one differential equation and two initial condition given. So what we did is the first step is taking Laplace transform on both sides. So we had this information in hand, that Laplace transform of first order derivative and Laplace transform of second order derivative. So with that we reduced our expression, and then in the last step what we had is Laplace transform of y is given by this RHS. So in the next step what we have to do is carry out inverse Laplace transform. So the process of inverse Laplace transform is what made it complicated, otherwise it is simple. So first of all you have to figure out a few known forms. So one known form was 1 by s, and the other known form is this 3 by s square plus 9, because they are Laplace transform of 1 and sine 3t respectively. So once you could figure out that, then you apply the convolution theorem, okay, to get the value of this inverse Laplace transform. So you got to know the inverse Laplace transform of this part is this, but there is also exponential involved. So you write whatever bit, like let's write it, like we know the inverse, this particular part, sub part is the inverse Laplace transform of this. So we wrote L of 1 minus cos 3t is given by this. And now we use the translational theorem. So using our translational theorem, we could easily conclude that whatever is lying inside is actually Laplace transform of some other function gt, which is given by this. So that actually, using that logic, we can say what is my value of y. So the process of calculating inverse Laplace transform is bit hectic, otherwise it's very simple. So similarly, in the next case also, we had this two differential equation, and we took in Laplace transform on both sides. And after that, it was basically like we have two simultaneous equation and we are solving them. So that's all. Like only the process we have to use our trick is what is the inverse Laplace transform of this function, that is cos t, that's a standard form, and sin t the standard form of the inverse Laplace transform of sin t. Yeah, so that is all about these two problems. So let me give a brief review. So it's already time is up, but let's have a brief review of what we did so far. So first part is the Laplace transform. This is the standard definition of the Laplace transform, and some important results. So these results are taken from the class notes only. So if you know these results, then it will be very helpful for your solving the problem. So then we went on to derive this form and also this form. So these are normal integration we used. Now we learn two properties of Laplace transform. One is linearity property, another is the translation property. So these two properties could help us solve these problems. So if you go back and check this lecture video, then you could understand how these two properties were being used to perform this particular problem, is to solve this particular problem. So we use those two properties and could easily arrive at the Laplace transform of a function, which was otherwise complicated. So next is the step function. The step function definition is this, like beyond certain threshold value it is 1, and below that it is equal to 0. So then also we learn to express a particular function in terms of the step function. So that is meant that the function is shifted by some distance, like the function is translated by some distance. So the Fourier transform of the Laplace transform of the translated function can be expressed as the Laplace transform of the original function by this logic, by this form. This property also was helpful a lot of times earlier, so it's very important. This property is very important. So next we got to express a function in terms of the step function, and then we use that property to find out the Laplace transform. The next was a periodic function. Now we did this inverse Laplace transform. We did this partial fraction method and split it into three known parts. Then the convolution operation. We did this convolution operation because it was helpful in finding out the inverse Laplace transform. And various properties of the Dirac delta. And how the Laplace transform can help us solve the differential equation. That is, we did in the last two problems. So I hope this lecture will be helpful in solving the assignment problem. So So in case you have any doubt, you can right now ask me, or you can either ask in the discussion forum itself. So yeah, hope to see you in the next session. So next session will be your last like problem live interaction session, problem solving. So after that, most probably you have your exams. Your exams is around like on which date? Like it will be on March, right? Okay, so yeah, 24th March. So today is 10th March. So 17th March we have this last problem solving session, and then 24th March will be your exam. Yeah, so go and look at this particular lecture, like on this Laplace transform, and that will help you solve the assignment problem. And then see you in the next class. All the best for your exam preparation and all. Yeah. Yeah. Thank you everyone for listening to this lecture. Bye. Stopping the recording.